we're going to talk about nuclides and isotopes. As it says here, a nuclide is any nuclear species with a specified mass number. Why would we need to specify mass numbers for our different atoms? That's because there exists something called isotopes. Isotopes are atoms of the same element that have the same number of protons, which obviously they would have to because they're the same element. Remember, protons identify that element that you're dealing with. But the number of neutrons can be different. Since those neutrons are neutral, you can have a varying number in the nucleus and it won't change that overall neutral aspect of the atom. So what are some examples of that? Well, hydrogen is one of the prime examples. Hydrogen has 3 isotopes: hydrogen, deuterium, and tritium. Hydrogen is by far 99.9% of all hydrogen is the one that has 1 proton in the nucleus, and that's all it's got. Along with its 1 electron, that gives us our normal hydrogen atom, the simplest atom that is in existence. But sometimes hydrogen has an extra or has a neutron in it, so we end up with 1 proton and then 1 neutron with that neutral charge, and we have deuterium, a different isotope. It's still hydrogen, but since it has a different mass number, it's a different isotope of hydrogen. The one that's radioactive is tritium. Tritium is pretty unstable. It doesn't really like having that extra neutron. So this one has 2 neutrons in it, and then that positive proton, it's still hydrogen. 1 proton means it has to be hydrogen, but it's another isotope since it has a different, once again, number of neutrons in it. We represent those differently when we show what we call nuclide symbols. If you'll notice here, these are what we refer to as nuclide symbols for these different isotopes, and they tell us information, basic information. If you look next in your notes, you can see that we can write symbols for any nuclide. That X right here stands for the chemical symbol, which is represented in hydrogen by the H. This A on top refers to the mass number. Remember, mass number is protons plus neutrons. And the B on bottom, the number on bottom, is the atomic number. And the atomic number, remember, is the number of protons only. So if you look up at these examples of nuclide symbols for our hydrogen isotopes, you'll see that the first one, since the top number is 1, that tells us that its mass number is 1. Obviously, the bottom number is going to be 1 because every single hydrogen isotope would have to have a bottom number of 1 because that's the protons. If it doesn't have a bottom number of 1, it's not hydrogen anymore. If it has a bottom number of 2, for instance, it would have to be helium. So the only difference in those isotope nuclide symbols is the top number, and that's because it refers to the mass number for that particular element. Since deuterium has 1 proton plus 1 neutron, the mass number is going to be a 2. Since tritium has 1 proton and 2 neutrons, the mass number is going to be a 3. So I kind of obscured those a little bit by my circles, but you see what I mean. That's what it refers to. So let's look at some examples of that. If we have carbon 14, for example, what does that mean? Well, writing a symbol for that particular isotope, that end number in the nuclide name is always going to be the same number that's on top in the nuclide symbol. So that's telling us the mass number is 14. That's the mass number. The bottom number we're always going to get from the periodic chart. Just simply look up carbon, see what its atomic number is, and that's going to be that bottom number, the number of protons. So 14 over 6, C, is the symbol for carbon 14. Notice something. Never put a division line between those two values. It's not done. There is no line between the mass number and the atomic number. So with that information, see if you can do uranium-239 really quick from your periodic table. So hopefully you paused this and looked at uranium. First of all, the symbol is going to be U for uranium, and we already established that the top number is going to be that 239, the N number in the symbol, or excuse me, in the nuclide name. And the bottom number comes from the chart, and if you look up uranium on the periodic table, you're going to find that it's 92. So that's the nuclide symbol for uranium-239. What if it asks you, given a particular isotope like uranium-235, it asks you how many protons and neutrons are in that particular isotope? Well, uranium-235, what does that tell us? Remember, this last number is protons plus neutrons. That's our mass number. We can look uranium up, we just did for the previous example, and found out that it had 92 protons. Look at it on the periodic chart. So it's got 92 protons. So how do we find out how many neutrons it has? We simply subtract. Our mass number minus the protons is going to give us our number of neutrons, because protons plus neutrons better give us our 235, which it does. So try the next one yourself real quick for barium-138. You'll do much better on all of this math if you will pause it like when I ask you to and try them yourself. It's a quick self-assessment to see if you're getting the information. So if you looked up barium, you know that the protons plus the neutrons have to equal out to 138. And barium, if you look up barium, has 56 protons. You look at it on the periodic table. So 56 protons. How do I know how many neutrons it has then? I'm simply going to subtract those 56 protons from the mass number, and that tells me that I have 82 neutrons. And 56 plus 82 better equal out to 138, which it does. The next section on your worksheet, when you do your worksheet, deals with writing the nuclide symbol and name for, in this example, samarium with 86 neutrons. Now, before we go any further, let me ask you, is that 86 neutrons going to appear anywhere on the symbol or name? And the answer to that is no, it's not. Are we going to need it to find those values? Yes, we are. But the 86 itself will never appear, and that's the most common mistake on the worksheet, is to put that 86 in for the mass number. That is not the mass number, that's the number of neutrons. So what do we know? We know if we look up samarium on the periodic chart, it's a weird one, we don't deal with it much, it's down at the bottom. Samarium has 62 protons. Well, what does that tell us? Well, that 62, as you notice, is going to be the bottom number. Remember, it's the atomic number from the periodic chart. The 86 is the neutrons. Remember, the protons plus the neutrons has to give us our mass number. And when we add 62 plus 86, like we did here, we end up with 148, and that's what goes in for that top number. Once we know that top number, the name is going to end with that, samarium-148. So with that information, see if you can do that last problem real quick, osmium with 111 neutrons. Pause it and see if you can do it on your own. Well, once again, is that 111 ever going to show up on any part of the nuclide name or symbol? No, it's not. We're going to need to use it, but it's not going to show up. So what do we know to begin with? Well, we know this is osmium and the symbol's OS. It's another weird one we don't see very often. And we know the name is going to start with osmium. If we look up osmium on the chart, we see that it's number 76. So we know that it has 76 protons, so that 76 is going to go on the bottom. So osmium has 76 protons. Yes. Plus the 111 neutrons, we can see that we're going to end up with a mass number of 187 for a mass number. So where does that 187 go? It goes at the top of the nuclide symbol and at the end of the nuclide name. So that's the nuclide symbol and name for osmium with 111 neutrons.